Hello, good evening to all of you, and welcome to Unacademy. Welcome to the NCERT series, where today we will talk about the interior of Earth and earthquakes. Now, basically, in the NCERT, this is the third chapter, and the book is Fundamentals of Physical Geography. Now, this third chapter has been broken down into two parts because the chapter talks about earthquakes as well, the chapter talks about volcanoes also, chapter talks about the interior of Earth also. So, rather than covering it in the same class where we are just brushing through it, I want to go deeper into the concept so that you are able to solve the actual previous year questions. I hope yesterday's session was something that all of you have watched, you have understood, and you have extracted the benefit out of yesterday's session. Today, again, keeping up with the trend, let us take a look at the PYQ that we shall be attempting after the coverage of the content. So, this is the PYQ of 2023 associated with the seismic waves. Consider the following statement. In a seismograph, P waves are recorded earlier than S waves. In P waves, the individual particles vibrate, so and so. We will take a look at it at the end of the topic, and let's judge whether we are able to solve this or not. Now, having said that, yesterday, based upon our discussion, I have two more PYQs for you, and let us see if we are able to arrive at the answer. So, this is the first PYQ of 2009. We are going slightly back, but then this was a question which was asked. In the structure of planet Earth below the mantle, core is made up of which of the following? This was a question. I expect you to provide the answer. So, we had discussed yesterday that basically core is composed of iron and nickel, and that is because of the stratification. So, that is where you will find that core is one of those portions, and we will also study that how it eventually leads to magnetic impact which is created across the planet Earth. So iron is the answer, right? I hope you know the logic also behind that. Now, another question which was asked in 2017. The terms event horizon, singularity, string theory, and standard model are sometimes seen in the news in the context of what? Observation and understanding of the universe, study of the solar and the lunar eclipses, placing satellites in the orbit of the Earth, origin and evolution of living organisms of planet Earth. So, here the answer is observation and understanding of the universe. The case of the event horizon, the theory of expanding universe, theory of Big Bang theory, all of that are associated with this aspect. Okay, so I hope we are continuing that trend of discussion of the previous year questions as well. And if you just follow this trend, trust me, your entire geography will be within your grasp before you know it. Now, coming to the topic, but before that, an announcement for all of you. Now, we have come up with a unique offer, a very student friendly offer, where, first of all, the lowest price ever, 16,999, which can be paid at a monthly aspect as well. And the unique part is if you do clear the UPSC prelims, you are eligible for 100% refund of whatever fees that you have paid. And in case that you don't get selected, let's suppose under any circumstance, in that particular situation, you will have the extension of your entire validity, and that will be on us free of cost. All that you got to do, use the code IS English. Okay. Now, without further ado, let us directly jump into the topic and let us directly jump into the first page of the chapter. So, here, yes, Binu, you can. So, here, basically, the chapter is the interior of Earth. Now, yesterday, what we had discussed about the formation and evolution of planet Earth, that becomes important for us to understand how the material inside the planet Earth is actually arranged. We had seen that when the planet Earth was solidifying, the cooling was happening, And it was actually the cooling from the outside, right? The outer portion started solidifying first. And that is where you had the weaker crust which was initially created, isn't it? And in the interior, you had the heavier materials which were situated, right? You had heavier elements. And then you basically had the lighter elements which were on the surface. Heavier elements included the case of iron and nickel. These were the heavier elements which were present. And which were the lighter elements which were present? You had the silicates, silicates of aluminium, magnesium, and so on. Now, by the way, when I say silicates, it does not mean only Si or silicon. Silicate refers to the oxide formation, right? Silicate generally refers to SiO2, right? So there is an oxide formation. Oxygen is also bound to the crust. Okay. So that is something that you will observe in the case of planet Earth. But then, for a long period of time, mankind had been very curious about what lied in the interior of planet Earth. The German geographers and then later on the American geographers, they had been pondering about it, that how do we understand what lies in the interior of planet Earth? There were multiple different types of experiments which were planned that let us dig so deep in the planet Earth that we are able to find out what is there in the interior. But then, beyond a certain depth, whenever mankind would start to dig, materials would be so hard that eventually the machinery would break. So, our understanding about the interior of Earth was always very restricted. It all started changing in the 1900s. That is why I always say that 1900s or the 20th century, especially the first half of 20th century, is a landmark in terms of discoveries which have happened about physical geography, about understanding the planet Earth, the climate, and also, most importantly, the human geography aspect was something which was understood in the 1900s. So, how do we know about the interior of planet Earth is something we will explore. But before I explore that, for all those of you who have the NCRTs with you, let me also tell you that here the first page talks about the interior and the sources of information. Second page here, while talking about the interior and not describing the crust core and the mantle, directly jumps into earthquake. Okay. Just because NCRT is unorganized does not mean we are going to be unorganized. We are going to go in a structural fashion. We will basically discuss the interior structure in detail. We will arrive at a conclusion and revise what is the interior structure, and then we will jump to the earthquake. So I will be revisiting this page after some part of our discussion as well. Okay. Now, first of all, what gives us an idea about what is present in the interior of planet Earth? So, the sources of information that we have broadly can be divided into two types: direct sources of information and indirect sources of information. On what basis do we divide this? Direct source and indirect source of information. Direct source, for example, anything which gives you the first hand information. I have dug the ground, I have found certain rocks, gives me an idea about what is there in the interior, isn't it? Volcano has erupted, it has brought materials from the interior, so gives me an idea about the molten material present in the interior. Those are direct sources. Indirect sources, I have to deduce it, I have to arrive at that conclusion. Okay. For example, let's suppose you have a friend. Now, whether that friend is punctual, disciplined, or not is something that you can see directly with your own eyes, your direct observation. What is the friend's character? That maybe others will tell you. So, that is an indirect source of information for you. Similarly, for planet Earth, what we can see with our own eyes, that is the direct source. So what is the case of the direct source? So majorly, there are three direct sources that we have. Volcanic eruption, right? So when you have molten materials bursting through the surface of planet Earth, and we know that planet Earth has been experiencing volcanoes ever since the phase of degasification, isn't it? So this volcanic material brings the, or this volcanic eruption brings the molten materials outside, gives you an idea what is present in the interior, right? Which kind of elements are present, what is the temperature, what is the particle density, everything we get an idea. Then you have the case of mining activities. When you carry out mining, dig the planet Earth for extraction of any element, gold, silver, coal, anything for that matter. You dig deep into the planet Earth, and that is where you are able to understand the type of rocks, the nature of rocks, and so on. And then you have digging. You go for direct digging as deep as possible in order to extract the maximum information. Now, through the mining, the deepest mine which was dug, for example, in India, you would have heard about the gold mining which was present in the KGF. If you have not heard about, at least you would have seen the movie or heard about the movie, right? So, Kolar gold fields would be for gold mining. Now, in the Kolar gold fields, we had dug up till 3.2 kilometer, quite substantial, isn't it? But the deepest mine which has been dug was not in the Kolar gold fields across the planet. If you are able to see the background image, this portion of planet Earth, this is known as your Kola Peninsula near the region of White Sea. Kola Peninsula. So, in this region of Kola Peninsula, we actually dug a mine, that is, humankind dug a mine, which was more than 10 kilometers up till around 12 kilometers deep. Now, overall, you could not have that great amount of activity in those mines, so that is why it is not counted many of the places. But some of the studies tell us that we had dug up till that depth. Mineable area was much lesser than that. But why could people not operate or not carry out the mining to that depth? The reason was very simple. As you would go into that depth, the temperature would get very high and materials would start to melt. People would not be able to survive. So, that gave us an idea that as you go deeper into planet Earth, temperature tends to increase. Temperature increases with depth. Okay. Now, this is a phenomena, even though not mentioned in the NCERT, but you should know about it. This is a phenomena which is known as geothermal gradient. Geothermal gradient. What is this geothermal gradient? Geothermal gradient is a terminology which is used to indicate the rise of temperature in the interior of planet Earth with increase in depth. Okay. Now, in what proportion does the temperature rise? So the temperature rise is something which is not consistent. It varies, but it is something which can increase by almost 20 to 25 degrees Celsius per kilometer. It can be that much. Okay. So temperature can rise in the interior at this particular rate. This is the rate. Okay. So that is why materials basically are very, very hot. Having said that, this is not common or consistent everywhere. It changes. In certain areas, it can be much less. In certain areas, it can be much higher as well. But these are your direct sources of information. Now, you also have your indirect sources of information. What are your indirect sources of information? From where you have to deduce. Okay. One is the case of seismic waves, which we will study in greater detail in today's class itself. Now, what are seismic waves? We will study that in great detail. But then, whenever an earthquake occurs in the interior, It will release energy. Okay. Let's suppose this is your planet Earth. Earthquake has occurred at a depth of, let's suppose, 100 kilometers. It will release energy. How much time does it take for that energy to shake the surface? So, with that information, you can always get an idea that, okay, what would be the depth, what would be the kind of material, and so on and so forth. Okay, so seismic waves have actually been the most important indirect source when it comes to getting an idea about how the internal structure of planet Earth actually is. Then you have something known as gravitational anomaly. What is gravitational anomaly? So basically, when we talk about the planet Earth is not a perfect sphere. It is a shape, what is known as an oblate spheroid, or in simple terms, a terminology has been invented for this, that is geoid. Okay, so planet Earth is what is referred to as a geoid. So, what is a geoid? Geoid is a shape whereby you will see that the planet is slightly flatter at the region of the poles and slightly bulged at the region of equator. Now, if you observe this image, here you will observe basically from the center up till the poles, right? The radius of planet Earth is around 6,356 kilometer. At the equator, the radius is 6,378 kilometer. So the radius is not consistent. The radius is changing. Radius is much more at the equator, much lesser at the region of the poles. So what does that mean? Simple terms. The gravitational pull that we experience will be different, right? Because gravitational force is indirectly proportional to or inversely proportional to the distance. For example, if you are closer to the sun, you will experience greater gravitational pull. If you are far away from the sun, lesser gravitational pull. So, gravitational pull is inversely proportional to the distance. So, if you are at the region of the North Pole, you will experience a greater gravitational pull because the distance is less. If you are at the region of the equator, you will experience lesser gravitational pull because the distance is slightly greater. So that means there is a difference in terms of the gravitational pull that you experience. That also gives you an idea about the shape and the structure of planet Earth, right? Then you have what is known as magnetic anomaly. Planet Earth behaves like a magnet in itself. But then that magnetic nature of planet Earth, that keeps on changing owing to Earth's rotation around its axis. Now, how it changes gives you an idea again about the interior. So, all these are inferred information. These are not your direct sources, these are your indirect sources. Then comes the asteroids and the meteors. How? So, asteroids and meteors, they are basically representative of the parts of the early solar system, right? Now, remember, in yesterday's class, we had discussed that in early solar system, you had multiple billions of particles which began to collide. And that later led to the formation of planetesimals, and that led to the formation of planet Earth. Now, asteroids, meteors, comets, these are basically the part of the solar system which have not become a part of a planet. So, what is the overall mineral constituency of these asteroids and meteors, these celestial objects? That gives you an idea about how planet Earth would have been created 4.5 billion years ago. Okay, so these are your indirect sources of information, which gives you an idea about the early part of the solar system and the time of the formation of the solar system. It is because of this that we get an idea that iron and nickel would have been very dominant in the early part of the solar system and the early part of the formation of protoplanet or the proto-Earth. Now, here, based upon this, we arrive at the structure of planet Earth. We are ignoring the earthquake parts. We are moving, first of all, into understanding the structure of planet Earth. Okay. Now, if you take a look at the structure of planet Earth, divided into crust, mantle, and the core. Okay. Those are your three major divisions: crust, mantle, and core. Now, the crust is the thinnermost portion, mantle is substantially thick, and core is in a molten state. So basically, if you take a look at the interior of planet Earth, you can always have an example that it is very similar to that of a coconut. Now, all of you would have seen the coconut. I'm sure you would not be able to see the interior of planet Earth, but at least a coconut is easily visible. Now, in the case of a coconut, what do you observe? The outer shell, the brown outer shell, it is the thinnest portion of the coconut, but it is very tough, isn't it? Now, if you try to exert force on this shell, the shell will immediately break. So, it is brittle in nature. It breaks immediately, right? It is not very thick, it breaks immediately. Then the coconut has got whitish flesh, right? Now, this whitish flesh, if you press it, it does not break, it gets compressed, right? So, rather than breaking, it deforms. Same is the case with your portion of mantle. And just like the core, just like the coconut, inner portion holds the liquid. Similarly, inner portion holds the liquid, and that is your core. So that is where you can always have a similarity between the Earth's interior to that of the portion of a coconut. It is not semi-molten. Core is molten. Okay? Liquid. Very much in a liquid shape. Okay? But it is not exactly like the coconut also. There is a variation. What is the variation? The variation you will see if you observe the interior of planet Earth. This is your portion of crust. This is the portion of mantle. This is the portion of the core. Now, core also has got bifurcations. This is your outer core, and this portion is your inner core. Okay. So, crust is solid, mantle is also solid, outer core is liquid, completely molten, but inner core is not liquid. Inner core is solid. Why? Let us understand the reason. Okay. The inner core is solid, and there is a very simple reason behind this. For example, let's take a block of iron. Okay. If let's suppose I provide heat. Okay. Now, as I provide heat, it will start to melt. It will form liquid iron. So, this liquid, what will be its volume? Much larger as compared to when it was solid. When it melts, it basically spreads. So, it will have a larger volume, isn't it? Now, this larger volume means when solid is getting converted into liquid, volume will expand. But what if I create a special circumstance whereby I ensure that this solid is not able to expand. I hold it from all different parts, okay, by stopping blocks, and then I heat it. Regardless of the temperature, it won't melt because it has got no place to expand. So it will remain in a solid state. Okay. So similarly, when you go to the depth of the inner core, from all the surrounding outside layers, the pressure is so high that the inner core has got no place to expand. So, despite the very high temperature and pressure, the inner core remains in a solid state because of the high pressure, and despite the temperature, the inner core remains in solid state because it has got no place to expand. So, why is inner core in a solid state? High pressure from the surroundings. High pressure from surroundings. Okay, doesn't allow it to expand. So that is why the inner core continues to remain in a solid state. And how did we get to know about this, by the way? No human has reached the portion of the outer or the inner core. No human has reached the portion of mantle as well. So how do we know about the portion of the outer core and the inner core? Based upon the study of seismic waves. That is why seismic waves become such an important phenomena and such an important indirect source in order to understand the case of interior of planet Earth. Okay? Now, this is your structure of planet Earth. If you consider the slice in the interior, average depth is roughly around 6370 kilometers. Now, you might have a query that you have said that the pressure is so high that inner core is unable to expand and is unable to melt. Then why is it that the outer core is in a molten state? Because even the outer core has got substantial amount of thickness, more than 1000 kilometers. So that 1000 kilometers of molten material will also exert a weight. And that is why by the time that you reach the inner core, temperature is always very high. And the pressure is also very high. Now, one other aspect I would like to talk about, basic aspect that we ignore. Why does the interior have very high temperature? Very high temperature. What is the reason behind this? We have been talking about it that interior has got higher temperature, interior gets very hot, materials get molten. But why is it that interior basically is of very high temperature? What is blocking the inner core? The pressure from the outer core, the pressure from the mantle, everything is not allowing it to expand. Okay. So basically, the interior has got very high temperature because of three factors. What are those three factors? First factor is what is known as residual heat. What is this residual heat? Remember yesterday's session when we were talking about the fact that planet Earth was cooling down from outside? So, as the planet Earth started to solidify, the heat in the interior could not escape completely. So, since the time of formation, Earth has trapped heat in the interior, right? So, that is why, since the time of solidification of planet Earth and the phase of cooling, Earth has managed to trap the heat in the interior. That is what is known as the residual heat. So, residual heat since formation, since the formation of planet Earth. Okay. Second factor. What is the second factor? In the interior, by the time that you basically reach the interior, there is a lot of pressure from surroundings. For example, let's suppose I take this pen. Now, if I start pressing this pen, my hands do not have that much amount of power. But let's suppose in some parallel multiverse, I have that much power that I could press this pen also. If you press this pen to great extent, it will get heated up, right? So that whenever you compress anything, there is a heat which is generated. So, planet Earth, as it had solidified, it had shrunk. So, that is where the temperature basically increased. So, this is basically where you have the case of compressional heat. Compressional heat. So, that is why as you move to the interior, the temperature tends to increase. Okay. Now, then after that, the third factor. Third factor is presence of radioactive materials. Active materials like uranium, etc. Now, these materials, they get decomposed, they break down, they undergo reactions, and as a consequence of those, they will produce heat, they will generate heat. So, these are your three factors which are responsible for the geothermal gradient of planet Earth. Okay, I hope this is absolutely clear for everyone. Now, let's discuss the layers of planet Earth. So, if you observe the thinnermost layer on the outside, that is your crust. Okay, that is what is referred to as the crust. And then underneath that, you have the portion which is your mantle and the core. As you can see, mantle is comparatively much thicker as compared to the crust. So let's start, first of all, with the case of the crust. Okay. So when you consider the crust, outermost part, solid, but it is brittle. It breaks very easily. Why does the material break very easily? I will tell you the logic behind that also. You will be able to understand the case of the earthquakes, volcanoes, etc. much easier in that case. But here, outermost solid part of the earth and is brittle in nature. But the crust is not of uniform thickness. The thickness of the crust underneath the continents is different from the thickness of the crust underneath the oceans. And also, when you see outside, you see the mountains, you see the large rocks, all of them are a part of the crust itself. But do you know that that is the lightest material which is present on planet Earth? So the next time that you see a mountain, don't get overawed by how large a mountain is. Always keep in mind that it is the lightest portion of planet Earth. If I would go into the depth, the materials would be much heavier, right? Just like your concepts in life, right? The cheaper ones always lighter in concept, the shallow ones. If I talk about the simple cases of countries, capitals, rivers, tributaries, not heavy. But if I start talking about the geothermal gradient, etc., heavy. Similarly, the interior of the earth also go into the depth, it becomes heavier. Now, this thickness of planet Earth, basically, you will observe that it varies whether you are in the case of the continental region or the oceanic area. In the oceanic region, the crustal thickness is only restricted to around 5 kilometers, right? But in the continental regions, it can be as much as 30 kilometers. In areas such as the region of Himalayas, the crust has been compressed to such an extent that it is as much as 70 kilometers thick. Okay. So always continental crust is going to be thicker as compared to the oceanic crust. Oceanic crust is always going to be very, very thin. So continental crust is thicker in areas of major mountain systems as much as 70 kilometer in the case of the Himalayan stretches. Okay, this is line by line from the NCERT itself. Okay, so not this one and not this one. But then, despite this fact, you will always observe that the continental crust is lighter. Continental crust is always going to be lighter. Now, and the oceanic crust is thicker. Crust is heavier, not thicker, heavier. Continental crust, it is thick, but it is light. This is thin, but it is heavy. Does it make sense? Think about it. It is very simple, guys. Imagine that you have a large block of thermocol. Thermocol, which is, let's suppose, 2 meters thick. Okay. And you have an iron slab, which is, let's suppose, 50 centimeter thick. Okay. So out of these two, this is your thermocol and this is your iron. Which is going to be heavier? Always iron is going to be heavier, isn't it? Despite the fact that it is very thin, iron is going to be heavier. Despite the fact that thermocol is very thick, still it is going to be lighter. Why? Because in a thermocol, you will find that the materials, they have lot of air in between. It is the density of materials. Density, how closely the materials are packed, that determines the thickness of it. Okay, if I have this plastic pen, it is this thin. If I have an iron pen, it will always be heavier, isn't it? So it is determined by the material composition, correct, and the density. So in the case of continental crust, it is made up of lighter and low density materials. Low density materials. Whereas this is made up of heavy density materials, or high density rather. So you will find continental crust, which is basically made up of granitic rocks, density of 2.7 gram per centimeter cube. In your 6th to 10th NCERT, this statement is given incorrect. So please correct it while you are referring to it. Even in this NCERT, when we will come to the portion further in the next chapters, this is given as incorrect value. Okay. Continental crust always has got low density. Oceanic crust has got a high density, 3 gram per centimeter cube. It is made out of basaltic rocks. Basaltic rocks basically are rich in iron and magnesium. Rich in iron and magnesium. Okay. Whereas continental crust rich in silicates of aluminium. Aluminium. Okay. This portion, I hope, is clear. Now, as we move ahead, I want to talk about the case of the mantle. Right. Now, in the portion of mantle, mantle is solid. Okay. So let me represent that in a schematic image. Let's suppose this is your outer surface. Okay. This is the portion which is your crust. Then let's suppose this is your mantle. And the inner portion is your core. Now, crust is solid, mantle is solid, core is molten. But then, this mantle is not uniform, by the way. As you move at a depth of around 160 to 400 kilometers from the surface, as you move at this depth, you come across a layer which is semi molten, right? Semi solid and semi molten. Okay. That is the layer that is semi solid or semi molten. Semi solid or semi molten. Now, this is your layer which is referred to as asthenosphere. Asthenosphere. Asthenos refers to something which is weak, and hence the name asthenosphere. Above it, mantle is solid. Below it, mantle is solid. Then why only in this portion it is semi-solid and semi-molten? And what do I actually mean when I say semi-solid and semi-molten? For example, imagine again, today's star of the show is this pen. So I again take the example of this pen. It is made out of plastic. Now let's suppose I start heating this plastic. Will it get converted into an absolute liquid? No, it will never get converted into absolute liquid. So if I heat this plastic, it will be stretchable, partially molten, and still partially remain solid also, isn't it? So that is the case, plasticky state, right? That is why asthenosphere very famously also is referred to as being in a plastic state, semi-solid, semi-molten. Now, why is that semi-solid, semi-molten condition existing? Because at that particular depth, you have certain elements which are not plasma, no. At that particular depth, you have certain elements at this depth. Okay, let me use a different color. At this depth, you have certain elements. Those elements are radioactive elements. Radioactive elements. Which are those radioactive elements? These are your uranium and isotopes of potassium. Isotopes of potassium. Okay? Don't simply say uranium, plutonium. I have seen many students, uranium, the next thing that comes to their mind is plutonium. So they blindly write plutonium. No. Isotopes of potassium. Now, these elements are experiencing a lot of heat in the interior. They are experiencing a lot of pressure also. That is where they undergo a thermonuclear reaction and that produces heat. They generate heat, right? Now, this heat which is generated, it partially tends to melt the materials immediately in the vicinity and above it. That is why these rocks, they do not consist of uranium or potassium. But because they are in contact with that heated region, they partially melt. Okay? Partial melting. This is the region of asthenosphere. Okay? So it is a clear cut distinction from the rest of the mantle. That is why you see many of the geographers, when they classify the interior of planet Earth, you know the classification that they do: crust plus upper part of solid mantle. This is what has been referred to as lithosphere. Crust plus solid part of upper mantle. Then underneath that asthenosphere, underneath that the lower mantle is also what is referred to as mesosphere. There's a mesosphere in the sky as well, but this is your internal portion. And then the molten portion of the core is also referred to as barosphere. Okay. So, this is the other kind of classification that you have about the interior of planet Earth: lithosphere, asthenosphere, mesosphere, barosphere. Right? But we will stick with crust mantle core. UPSC requires average aware graduates. Let's be average. I'm sure all of us are. Let's be aware in this particular case. So, crust mantle core, but in that mantle, you will have the case of no inner portion of core, some part of outer core, and inner portion of core. Okay. So, in the mantle, you have asthenosphere. Okay. Let's then come to the NCERT writings. Portion of the interior beyond the crust is called as mantle. Okay. The mantle represents about substantial amount of Earth's mass. The density tends to increase. Remember, in the crustal portion, what was the case? Crustal portion, density was 2.7 gram per centimeter cube in case of continents, and the case of oceans, you had 3 gram per centimeter cube. Okay. Now, in the case of the mantle, it further increases. As you go into the lower portion of the mantle, it tends to further increase. Okay. Now, asthenosphere. Upper portion of the mantle is known as asthenosphere. The word astheno refers to weak, right? It is considered to be extending up till a depth of 400 kilometers. It is the main source of magma, the molten materials which come to the surface during volcanic eruption is actually provided by this asthenosphere. Okay. Repetition of mesosphere and barosphere. Simple. Crust plus solid portion of upper mantle, lithosphere. Underneath that lithosphere, the case of asthenosphere. Below that asthenosphere, lower portion of mantle and some part of outer core, mesosphere. And then the extremely heated portion of inner core and some part of molten outer core, that is your barosphere. Okay. Now, this is the portion of asthenosphere. We know now the reason why asthenosphere has got substantial amount of heat. It is the pressure exerted on the radioactive elements. Which are the radioactive elements? Uranium, isotopes of potassium. Okay. We do have the portion of molten, the solid mantle above it. Look at this image. Okay, look at this image, the side image. This is your portion of the crust, isn't it? Now, there is some portion of mantle which is above the asthenosphere, the one that I have shaded. Okay. So, this portion is solid, solid, right? Just like here. This is your solid portion. This is also your solid portion. So, above that asthenosphere, you have the solid mantle. That is what together combined is known as the lithosphere. Okay. Now, the difference between crust and mantle when it comes to how they behave when they experience forces and pressure. Very simple, expressed by this particular analogy and image. If I keep an iron rod at room temperature and if I hit it with a hammer, what will happen? It will break, right? Suddenly, that is where excessive force is applied. It breaks, isn't it? But if the same iron is heated at a very high temperature, okay, the iron is at a very high temperature, almost semi molten, or not semi molten also, but very high temperature, glowing red. If I hit it, it will get deformed, isn't it? It will not break, it will get deformed. That is how your the ironsmiths, etc., they make the tools, iron tools, by hitting the heated iron. Now here, this iron has not broken, it has got deformed. This iron has broken. Crust is at lower temperature. Crust is the coolest portion of planet Earth. As you move in the interior, the temperature increases. So mantle is at a much higher temperature. Because mantle is at a much higher temperature, it will get deformed rather than breaking. So breakage and brittleness is associated with the upper portions of Earth. Lower portions, deformation, compression, expansion is associated with the lower portion. I hope this is another fact which is cleared. Then we come to the portion of the core. Now, core, the innermost portion. So here, inner core is in the solid state. The core starts at a depth of 2,900 kilometers. Inner core is in a solid state, whereas the outer core is in a liquid state. Inner core is in a solid state. Why? Because the pressure from the outside is so very high, it is unable to melt. Okay. Now, here, core is made up of very heavy material, mostly constituted by nickel and iron, and that is why also referred to as the Nephi layer. A quick recap: crust, the lightest portion, that is the portion of your crust, solid portion of upper mantle. Then, within the upper mantle itself, there is the asthenosphere. Now, in case you are getting confused, that in asthenosphere also you are saying upper portion of mantle, in lithosphere also you are saying upper portion of mantle, which is correct? So please understand one thing. Mantle has got a thickness of 2,800 kilometers. Thickness of the mantle is 2,800 kilometers. So if I consider something which is at a upper portion, it will also be upper portion of mantle. If I consider something which is at a depth of 100 kilometers from here, or 200 kilometers from here, it will still be the upper portion of mantle, because mantle in itself is 2,800 kilometers thick, isn't it? So lower mantle is solid, upper mantle is solid. Just in between, asthenosphere is semi molten and semi solid. Right? I hope this is clear. Right? Now, then comes the portion of earthquakes and seismicity. Now, earthquakes, they basically have been occurring across planet Earth since the time of its formation. And it has disturbed humankind for the longest duration. Okay. So, when we talk about earthquakes, why does the earth shake? Why does the earth shake? So, here, let us depart from what is written here and let us understand it in an image form. This is my only grievance with NCERT, that it does not provide you enough images that you can understand it easily. So, let us understand this easily. Let's suppose this is your portion of the surface, interior. Now, if you apply forces on this interior, it will bend to a certain extent, but not always. Right? If I take a piece of paper, I extend force on it, the paper can bend. But if I take this pen, I apply force on it, it will not bend, it will break. So when excess forces are applied on the interior, it breaks. And then any kind of movement, sudden movement in the interior, releases an immense amount of energy. And that leads to the shaking of the earth's surface. And that is what we refer to as an earthquake. Okay. So, this interior, the point from where energy for the first time is released, is known as the focus of the earthquake. Okay. And immediately above it, you have the epicenter. Okay. So when an earthquake, so basically, Earth's crust is slowly bent due to the internal forces, which keeps on building the energy. Eventually, it will break. Eventually, when it breaks and the sudden release of energy which happens, that shakes the Earth's surface, and that is known as an earthquake. Okay. So that is basically the case of an earthquake. Origin of an earthquake, focus. The reference point on the surface, epicenter. Epicenter is exactly above the focus. Exactly above the focus. So, why do we have this epicenter? So that you have a point of reference on the ground surface, that where did the earthquake actually occur? Okay, in which place did the earthquake actually occur? Now, how do we measure this earthquake? There are various ways to measure the earthquake. There is a device which is known as a seismograph. Seismograph. Okay. Now, in this seismograph, you would observe these kind of readings. You actually have a drum, a paper drum, where you have the paper drum which keeps on rotating and a pen is kept. Any shaking or vibration on the earth's surface, the pen starts to move. And that is what is charted out here. Okay. So that is how basically you measure that how much amount of energy is basically released. Okay. But there are various concepts about measuring of an earthquake. Let us understand that. So, how do we measure the earthquake? You see, this seismograph and all, these are modern inventions of the 20th century. But imagine 2000 years ago, or 1000 years ago, or 500 years ago, or even 200 years ago. If an earthquake would occur in a region, now, would people be able to measure the amount of energy? No. People would always see the amount of destruction. That, that earthquake which occurred, the buildings also fell down. And they would have a reference that as compared to the previous earthquake, this was stronger because in the first earthquake, only the trees were shaking, some movement was there, but nothing fell down. So, based upon the damage which was caused on the surface, they would gauge the earthquake, right? So, that is something which is known as intensity. What is the intensity of an earthquake? So, intensity takes into account the visible damage caused by the earthquake event. It is measured by what is known as a Mercalli scale, right? This is your Mercalli scale. It is basically up till the intensity of 12, right? 12 means everything has been destroyed, right? So, 1, intensity 1, nothing was felt. Only few people felt it. 2, 3, some people have felt it while they were awake, right? Then 4, you would have felt it. Some objects would have also moved. So, based upon the perceivable damage, when you measure the earthquake, it is known as intensity. This is measured with the help of what is known as Mercalli scale. Now, this Mercalli scale would have the reading 1 to 10, but later on it was modified, okay, to add two more values. And that is where it was extended to 12. So now you measure intensity with what is known as the modified Mercalli scale, which varies from 1 to 12. But you see, the destruction which is caused by an earthquake, now that destruction is something which is basically depending upon the region, depending upon the depth from where the earthquake has originated. A focus can be 10 kilometers deep, a focus can be 60 kilometers deep, a focus can be 100 kilometers deep, right? Similarly, a region which has got multiple buildings will have more damage as compared to an open farmland. So damage is something which depends from one region to another. So the classification based on the damage, that is intensity, is not a very good classification. You actually need to measure the amount of energy which is released in an earthquake. That is when the classification actually becomes meaningful. Now, how do you measure the amount of energy released? So you see this graph, wherever there is greater amount of deviation, that means more energy has been released, isn't it? So that is where you would observe that basically the energy released is measured by something which is known as the magnitude of the earthquake. Okay, it is known as the magnitude of the earthquake. This is something which is measured on a Richter scale. Richter scale measures the energy released during an earthquake. Okay, so here variation from 1 to 10, an earthquake more than 9 has never been recorded. One thing that you have to keep in mind for your exam is that this Richter scale is logarithmic in nature. Logarithmic. What do we mean by logarithmic in nature? Basically, an earthquake of magnitude 6, let's suppose, earthquake of magnitude 6 is going to be 10 times, is going to release 10 times more energy as compared to earthquake of magnitude 5. An earthquake of magnitude 7 is going to release 10 times more energy as compared to earthquake of magnitude 6. Okay, so 6 is going to release 10 times more energy, okay, as compared to 5. That is the case of the Richter scale. Okay, now the classification of earthquake, one of the classification of earthquake is the based upon the depth. Where did the earthquake originate from? Did the earthquake originate at a great depth, lower depth, or closer to the surface? Based upon the depth, you have the classification as shallow focus earthquake. Majority of the earthquakes which occur across the world, from your Venezuelan earthquake to many of the Himalayan earthquakes to the case of the Turkish earthquakes, all of those, they are majorly shallow focus earthquakes. In this, the depth of the focus is around 0 to 70 kilometers. Then intermediate focus from 70 to 300 kilometers. And furthermore, greater than 300 up to 700 kilometers. Deep focus earthquake. Beyond 700 kilometer, focus does not lie. No earthquake will occur at a depth beyond 700 kilometers. Why? If the depth of planet Earth is almost 6,400 kilometers, why are earthquakes restricted only up till 700 kilometers? That is not even 1/8 of the depth. The reason being, as you move into the greater depth, temperature increases, right? So beyond 700 kilometers, temperature increases. As the temperature increases, then remember this particular aspect that we talked about. If the temperature is high, materials will get deformed rather than break. So if the temperature gets very, very high, materials will get deformed, they will not break. That is why beyond that particular depth, beyond the depth of 700 kilometers, you will find that materials get deformed and do not break. Okay? Get deformed, but don't break. And if they don't break, then obviously no movement. No movement means no focus, no earthquake, no epicenter. That is why this is again one of the basic fundamentals of the case of the earthquake and how the earthquake occurs. Now, whenever an earthquake occurs, it releases energy. Energy always travels in the forms of waves. For example, let's suppose light. Light is also energy. So, light also travels in the form of waves. Sound. Sound is also energy, right? It also travels in the form of waves. So, just like when energy is released, okay, whenever energy is released, it travels in the form of waves, and that is what is known as seismic waves. So, seismic waves are the waves which are released during and whenever an earthquake occurs. Now, these seismic waves are of two types: body waves and surface waves. What is the difference? What is a body wave? How do we know what is a body wave and what is a surface wave? Before coming to this diagram, understand this. Let's suppose this is the surface. Let's suppose at a depth of 70 kilometers, an earthquake has occurred. Now, this earthquake, when it has occurred, it will release energy, it will cause vibrations here. Now, this energy is traveling through the body of planet Earth, and that is what is known as body wave. So, the energy waves which travel through the body of planet Earth, body waves. Once they hit the surface, then the surface will start to shake. So, that is your surface wave. So, waves that move through the interior of Earth, body waves. Waves that only travel along the surface, surface waves. But more destruction is always caused by the surface waves. Always. Surface waves is going to create much more amount of destruction. Always. Why? I will tell you that also. But these seismic waves, they are further classified. So here, if you observe, basically, see, this is the case of the body waves, right? And the surface waves get generated. So there are two types of body waves. All this NCRT has basically compiled in this paragraph: propagation of earthquake waves, etc. It is from this section that UPSC had extracted the question that we had put up in the initial portion. That is why careful reading of NCRT is a must. Anybody who teaches you NCRT and simply browses through it, try to get into the depth of it. Okay, each sentence in the NCRT is worth an hour of discussion in itself. Okay, so here, first of all, the seismic waves classified into two types: body waves, surface waves. Body waves further classified into two types: P waves, S waves, and surface waves classified into two types: love wave and Rayleigh wave. Okay, now, by the way, body waves have much greater classification also beyond the scope of the NCRT, so we are not covering that. Body waves are further classified into PS, PG, and multiple different other types of waves also. But for simple aspect, we will understand P waves, that is primary, S waves, that is secondary. Okay. Surface waves of two types: love wave, Rayleigh wave. Nothing to do with the idea of romance. Love wave, very destructive, basically named after the scientist, right? Rayleigh also named after scientist. Okay, so that is how you have got the naming. But what is the difference between a P wave and an S wave? Understand this. Now, let's suppose this is the point from where, let me represent this surface. This is your focus. From here, basically, energy has been generated. Okay, energy has been released. So, this energy which is released, it will push the materials closer. expand it also. Just like a spring, if you hold the spring, you release it, right? There will be compression, expansion. So the particles, the movement of the particles, it will be a compression, expansion, compression, expansion. If I show you the animation of this is your P wave. Observe the second wave one. Observe the second one, second animation. Compression, expansion, compression, expansion. Isn't it? Now, what is the direction of the wave? This is your direction of the wave in both the cases of wave, seismic wave. What is the direction of the particles? Direction of particle is this, of particles. So direction of particles is same as the direction of the wave. That is why they end up moving very fast, right? P waves are the fastest. Why? Because particle motion, direction of particle movement is same or parallel, is same as direction of wave. Okay? Same as the direction of the wave. That is why it moves so quickly. Now, you have the case of the S waves, which are comparatively slower. Why? Because in this, the particles move differently. If you observe, this is the representation of your S wave. Now, what is the direction of the wave? Wave is moving like this, in this direction. But how are the individual particles moving? If you pay attention to only one section, let's suppose I pay attention to this section. Let's observe how the particles move. They move up, then they move down, then they move up, then they move down. Isn't it? Again, observe this. This particle is moving up, down, but the wave is moving in a different direction. So, in the case of S waves, direction of particle movement is perpendicular to direction of wave motion. That is why it is slower. Now imagine if you consider liquid. Particles are far away in a liquid. In solid, the particles are much closer to each other. So in a solid, it can easily be achievable. This kind of a wave motion can easily be achievable. But in a liquid, it won't be achievable. Maybe this particle will be disturbed. Second particle may be slightly, but third particle won't be disturbed at all. Isn't it? That is why S waves are not able to travel through liquid medium, whereas P waves, they will be able to travel through liquid medium also. Okay. Why? Because if I consider liquid, particles are far away. But if this portion gets disturbed like this, second particle will be hit, third particle will be hit. To best way to understand the P waves, remember your school days when you were standing in line. Last person in the line would fall and the front person would also get disturbed, isn't it? Then basically imagine the time when you would stand in line and queues for, I don't know whether your generation has done it or not, when you would stand in queue for the theaters or any of the music show. Regardless of the distance that you have, someone behind you will fall, you will also fall ahead. That is your P wave. Regardless of the distance, regardless of the condition, it will travel. S wave is like if you are standing in line, somebody peeps on the side, you might not peep, right? So that is where S wave does not propagate if it is distant enough. But if everyone is very close together, in that particular case, someone peeps, Next person will also try to see what is this person trying to see. The third person will also then bend over. So S waves are like that. If everyone is close together, S wave travels. Okay. I hope this is basically understood. Now, once the surface basically gets disturbed, just like water, if you have water, if you would have done this in your childhood days, you throw stone in water. Now, water is calm. You have thrown a stone. Stone will hit one portion, not the entire lake or pond, but that will send ripples all across the water body, isn't it? So, even if this is your epicenter, let's suppose, epicenter, it has been disturbed by the body waves. But once it is disturbed, then the surface gets disturbed. This is your surface wave. Surface waves are also of two types depending upon how the surface tends to behave. If the surface moves horizontally, love wave. If the surface moves vertically, then it is Rayleigh wave. Okay? Surface tends to behave in, or surface tends to move in both direction. It will be like this also. It will be like this also. So why do I say that surface wave is more destructive? Imagine this is the building. Okay? P waves have shaken the surface and the surface is shaking like this. Building is not going to fall. S waves are shaking it horizontally. Building might withstand it. But when surface wave comes, then what will happen? The building will never be able to withstand this. That is why surface waves are always associated with greatest amount of damage. Okay. Now we come to the final topic, and that is the case of the shadow zone. So, as I told you, the seismic waves help us understand how the P waves have traveled, how the P waves have moved. That helps us understand the interior of planet Earth. How? For example, if let's suppose I know the property of the P wave, okay, I know the speed of the P wave. Now, if P wave has taken 10 minutes to reach this area, this distance, I know the density of material through which it has traveled. If I know the property of S wave also, I calculate the time duration. I get to know the density of material. So, like that, the P wave and the S waves, they give us an idea about what is present in the interior of planet Earth. However, these body waves, they do not distribute themselves uniformly in the interior. They bend, as you can see, they bend, and they have a kind of a unequal path. And that means if an earthquake has occurred here, even if I install seismographs all around the planet Earth, I will not be able to detect the earthquakes in certain areas. I will not be able to experience or detect these S waves in certain areas. So, that is basically the concept of a shadow zone. Now, how to understand this concept of a shadow zone? So, basically, you would have studied in your childhood days the basic property of light. That light, when it hits the glass, it bends, and again, it bends when it comes out of the glass. Now, why does the light bend here? Because light has encountered material of a different density, isn't it? So, when any energy comes across materials of different density, its speed changes and it bends. In the interior of planet Earth, also, when you go from crust to the portion of the mantle to the portion of the core, within that also the density changes. So, as it travels, it encounters materials of different density. S waves will encounter the core also. Now, can core, which is in liquid state, Can the core allow the S waves to pass through? No. That is why S waves are absent in the region of the core. So observe this. Observe this case. As the P waves encounter materials of different densities, they will naturally bend. They will naturally bend, right? They can pass through the outer liquid core as well. But then, in the case of S waves, the moment the S waves detect the outer liquid core, S waves go silent. That is why, in an earthquake which has occurred, let's suppose at this location, at an angle from 105 degree to 105 degree on the other side, no S wave is detected. That is the shadow zone of the S wave. In the case of the P wave, from 105 to 145, no P waves are detected. That is the shadow zone of P waves. Okay, just to clarify this, for example, if this is the planet Earth, not a perfect sphere, but nonetheless, let's suppose the earthquake has occurred here. Shadow zone of P wave will be here, and shadow zone of S wave is going to be much larger. Now, why is it that shadow zone, they can't travel in the interior? Why? Body waves, they always travel in the interior. That is why they are known as the body waves, because they travel in the interior. If they travel on the surface, they are known as the surface waves. Okay. So, why is the case that shadow zone of S wave is larger than the shadow zone of the P wave? What is the reason behind it? Simple. S waves cannot travel through liquid medium. That is why S waves are unable to, or S waves are unable to move to the region of outer core. Hence, the shadow zone of S waves are higher. Shadow zone of S wave is larger. Why? The reason: can't travel through liquid outer core. Okay? Any doubt in this till now? I hope this is clearly understood. Then you also have the case that types of earthquake. How do the earthquakes occur? So, earthquake can occur because of the fact that, let's suppose, there is a disturbance on the lithosphere itself, right? Lithosphere gets broken, tends to move, like you had in Venezuela, like you have in Himalayas, and so on. So, that is where these are known as the tectonic earthquakes. Sometimes during the volcanic eruption, volcanoes is something that we will study tomorrow in detail. So, volcanic eruption can also lead to disturbance as molten materials try to emerge and erupt through the surface. They will hit the surface, they will shake the surface. Volcanic earthquake. Sometimes where mining activities are being carried on. In that case, if the roof collapses, the earth shakes. In the area of the mining regions, many of the times you also have the case in mining areas, controlled explosions are carried out in order to loosen the rocks, etc. That also creates earthquakes, right? So, for example, if any of you are from the mining towns of the country, you would have observed those earthquakes twice a day. The earth shakes in that local region itself, right? Then you also have the unique case, what is known as reservoir induced seismicity. Now, what is that? Earthquake, basically, P waves move through all medium. Yes, correct. Earthquake which has occurred because construction of a dam or a reservoir. Now, let's suppose this is the land. I have constructed a large dam. Now dam will pile up lot of concrete. This will put in lot of weight on the rocks. The rocks get deformed, isn't it? Plus, it will store millions of gallons and tons of water. This water will also impose lot of pressure on the rocks. As a consequence, the rocks tend to develop certain cracks. And any movement within this is going to lead to earthquake. That is why in areas prone to earthquakes, it is suggested never to build large dams. But this is what China is doing by constructing a very large dam in this area, around the region, around the river of Brahmaputra. Okay. Bhakra Dam got tilted because of different area reason, because of the siltation process. Okay. But you have the case of Koyna Dam. Koyna Dam across river Koyna. Koyna is the tributary of which river? Let me know in the comment section. So Koyna Dam disaster was caused because of this particular reservoir induced seismicity. So even humans can cause earthquakes. Nuclear explosion will always cause an earthquake. Okay. Now that brings us to the end of the chapter here. Now let us solve this previous year question. In a seismograph, P waves are recorded earlier than S waves. In P waves, the individual particles vibrate to and fro in the direction of the wave propagation, whereas in S waves, the particles vibrate up and down at right angle to the direction of wave propagation. Which of the statements given above is or are correct? I hope we know that P wave is faster, right? And also, we have seen direction of particle motion and the direction of wave propagation. This is also correct. So the correct answer is C, 1 and 2. Okay. So that brings us to the end of the discussion for the day, where we have covered interior of planet Earth and also the case of the portion of the earthquakes in as much detail as it is required. And you would have seen this with the help of the previous year question as well. If you have liked the session, don't forget to click on the like button, share it with your friends, and also help them understand the importance of NCRTs and importance of developing the concept. Okay. You don't need to buy the NCRTs. We are going to cover it here as well. So do share it with your friends. Put your overall experience in the comment section. And tomorrow we meet again. And tomorrow we are going to discuss about the volcanoes that are experienced across planet Earth. So thank you all for being patient. See you tomorrow. Take care. Goodbye.